eukaryote comes from the Greek for true nut. They have an internal skeleton that provides structural support and shuttles molecules from place to place. And they have mitochondria, bean-shaped power stations that supply cells with energy. All eukaryotes share these traits because we all evolved from a single ancestor, around 2 billion years ago. Before that point, life on Earth could be divided into two camps or domains: the bacteria, which we already know about, and the archaea, which are less familiar and have a fondness for colonizing inhospitable and extreme environments. These two groups both consisted of single cells that lack the sophistication of eukaryotes. They had no internal skeleton. They lacked a nucleus. They had no energy-providing mitochondria for reasons that will soon become abundantly clear. They also looked superficially similar, which is why scientists originally believed that archaea were bacteria. But appearances are deceptive. Archaea are as different from bacteria in biochemistry as PCs are from Macs in operating systems. For roughly the first 2.5 billion years of life on Earth, bacteria and archaea charted largely separate evolutionary courses. Then, on one fateful occasion, a bacterium somehow merged with an archaean, losing its free-living existence and becoming entrapped forever within its new host. That is how many scientists believe eukaryotes came to be. It's our creation story. Two great domains of life merging to create a third in the greatest symbiosis of all time. The archaean provided the chassis of the eukaryotic cell, while the bacterium eventually transformed into the mitochondria. All eukaryotes descend from that fateful union. It's why our genomes contain many genes that still have an archaeal character and others that more resemble those of bacteria. It's also why all of us contain mitochondria in our cells. These domesticated bacteria changed everything. By providing an extra source of energy, they allowed eukaryotic cells to get bigger, to accumulate more genes, and to become more complex. This explains what biochemist Nick Lane calls the black hole at the heart of biology. There's a huge void between the simpler cells of bacteria and archaea and the more complex ones of eukaryotes, and life has managed to cross that void exactly once in 4 billion years. Since then, the countless bacteria and archaea in the world, all evolving at breakneck speed, have never again managed to produce a eukaryote. How could that possibly be? Other complex structures, from eyes to armor to many-celled bodies, have evolved on many independent occasions, but the eukaryotic cell is a one-off innovation. That's because, as Lane and others argue, the merger that created it, the one between an archaean and a bacterium, was so breathtakingly improbable that it has never been duplicated, or at least never with success. By forging a union, those two microbes defied the odds and enabled the existence of all plants, animals, and anything visible to the naked eye, or anything with eyes for that matter. They're the reason I exist to write this book and you exist to read it. In our imaginary calendar, their merger happened sometime in the middle of July. This book is about what happened afterwards. After eukaryotic cells evolved, some of them started cooperating and clustering together, giving rise to multicellular creatures, like animals and plants. For the first time, living things became big, so big that they could host huge communities of bacteria and other microbes in their bodies. Counting such microbes is difficult. It's commonly said that the average person contains 10 microbial cells for every human one, making us rounding errors in our own bodies. But this 10-to-1 ratio, which shows up in books, magazines, TED Talks, and virtually every scientific review on this topic, is a wild guess, based on a back-of-the-envelope calculation that became unfortunately enshrined as fact. The latest estimates suggest that we have around 30 trillion human cells and 39 trillion microbial ones, a roughly even split. Even these numbers are inexact, but that does not really matter. By any reckoning, we contain multitudes. If we zoomed in on our skin, we would see them, spherical beads, sausage-like rods, and comma-shaped beans, each just a few millionths of a meter across. They are so small that despite their numbers, they collectively weigh just a few pounds in total. A dozen or more would line up cozily in the width of a human hair. A million could dance on the head of a pin.